My name is Peyton Kutcha. I'm your room captain for Theater 2 today, your guide through this event. Thank you for coming to SAS Innovate. I hope you're enjoying your day 3. We're so happy to have you. We've got an amazing presentation today from Nate Cox and Nassim Rahimi about DOE meeting synthetic data. They've got a variety of experiences and several years of experience in this process and in this project. So they are the best to bring you this kind of presentation. And with that, I'm going to pass it on to them before I talk them up too much.
Hi everyone, welcome to our super demo. My colleague Nate and I, we are so excited to be here to talk to you about our patent pending application we developed, which is enhancing design of experiment with synthetic data. So first, we're going to talk about, okay, what is design of experiment and how you call it good or bad, and the use case we developed to showcase the capability. Then we talk about what is synthetic data, how the synthetic data augments our data, and then we show you an analysis that we've done in Voya with a really great AI ML that shows the traditional versus the advanced modeling. So just to give you a big picture before we get technical, design of experiment is when you have a systematically designed bunch of experiments to accomplish a study between factors and levels and see the impact of that on responses of a process or an outcome of the process. I'll explain more in detail what that exactly means, but that's a common practice in pretty much all industries. And as you know now, listening to Innovate for 2 days now, that synthetic data is the data you generate from a real world data, but it's a data that you generate using math and algorithm and Gen AI behind the scene. So it's mimicking the real world data, but it's a synthetic data. And when you marry both, and you use Voya for analysis, you can unlock a lot of capabilities. First of all, you can imagine these experiments take a lot of time and effort, right? Before joining SAS, I was engineering manager, and sometimes it takes over a year to conduct a single design of experiment if you're improving a product or process. So if you be able to augment that data with synthetic data, you considerably reduce the cost because you don't need to go through all that resources and effort, to collect that data. And no matter what you do, you never can consider all the scenarios. So your data ends up always being limited. And you can have a much faster insight that way because you generate synthetic data really quickly based on a smaller sample data that you collect from the lab. And then you have a much wilder exploration because now you can simulate, extreme conditions, rare cases, things that you cannot replicate in a lab. Let's say very extreme temperatures or like materials that you don't have access to. And because now we augmented the data with synthetic data, you have a much bigger data set that your modeling is going to be much more accurate. So that's the big picture. But what do we mean by design of experiment? For some of you that might not be very familiar with that, if I want to simplify and kind of tell you the terminology we use in the engineering world, think about making a cake. Think about you don't have a recipe for a cake you want to make, or you have a recipe and you're like me, don't like it too sweet, you want to cut the sugar. But you don't know, you can't just cut the sugar, right? Because it's gonna affect the texture. So you have to go through a bunch of experiments. Hey, I'm gonna, cut the sugar, increase the oil, what's the oven setting should be. So all these factors, variables that goes to your experiment are factors. And all the levels, like how many cups of sugar, how many eggs, what's the oven setting. These are called levels in the design of experiment. And the outcomes and characteristics that you are measuring, they are called responses. In the cake example, it can be the sweetness, the texture, fluffiness, what you're expecting to get out of a cake. So that's the definition of design of experiment. So you can think that applies to pretty much everything in life, right? And you can think how time-consuming and expensive this can be. Think about making a cake. If you want to have an optimum recipe, you have to use a lot of ingredients, go through a lot of different combinations. You can never try all possible combinations. What are the increments that you're gonna go about, your ingredients? And at the end, you have to kind of compromise, have something good enough that you're happy, but that's not the global optimum. So that's similar to the real world case scenario when you do design of experiment. And as I mentioned, that's used across all industry. You name it, like from discrete and process, pharmaceutical and healthcare, semiconductor, chemical, gas, oil, everywhere across the world, they do design of experiment when they want to design a new product, change a product, they want to change a process for many different applications. And the way we do this traditionally is, okay, I'm as an R&D engineer, I describe what's my desire, what's the problem, what's the product, what's the process I want to change. I specify the factors, the levels, and the responses, and then I go to traditional softwares like JUMP, SAS, you can code it with MATLAB, Minitab, different softwares. Industry standard a lot of times is JUMP, and I give all these factors, levels, and responses to the software. The software, based on the physical method I choose behind the scene, depending on my application, gives me a set of experiments that, hey, go to the lab, put all these settings, use this material, and measure the responses. Then you collect that real-world data from the lab, go back, plug it to the software. Traditional way, the software fits it, and you have very limited number of observations. Like it can be tens, it can be hundreds. And then you fit it, and you try to predict and optimize that limited data. So what we changed in this process, we did the first 3 steps the same way. So we defined our use case, we designed it through JUMP, we collect the data. In this case, because we didn't have lab, we simulate the data with math, and we added error function to make it probabilistic rather than deterministic to kind of hide the correlations and everything. And then we augmented that data that resembles the data you collect in a lab with synthetic data using DataMaker. And then instead of going back to this desktop application softwares, we went to SAS Vaya. And we use the AI ML applications and capability of Vaya now to do more in-depth analysis and do optimization, not based on traditional statistical methods, but based on deep learning. And in case of understanding how we improve design of experiment, we have to understand the metrics that we use to measure the goodness of design of experiment. So we have something called desirability function. And the way you need to think about it is all these responses that you have in design of experiment, they compete with each other. You want to minimize, the other one you want to maximize, the other one you want to set at a specific number, and a lot of times it doesn't happen at the same time. So you have to kind of compromise. So there is a math behind the scene that assigns a number between 0 to 1 to all these responses you want to optimize. And 1 meaning the most desirable outcome, and 0 meaning the terrible outcome. So you want each single response to have a desirable function that's close to 1, but also you have an overall desirability of looking at all these responses together, that you want that overall desirability also to be close to 1, which is a geometric mean of all these responses. So forgetting about the technical jargon, think about, okay, there is a mathematical goodness that we call as desirability function, and we want it to be close to 1. And when my colleague Nate shows you Vaya in action, he's going to talk about this a lot. So keep that in mind, that this is the definition. And to show the capability, we had to come up with a use case, right? We had to define a use case and show traditional versus the modern way. So this use case we are introducing is thermal management for HAMR technology. HAMR is a heat-assisted magnetic recording, which is a technology that hard disk drive manufacturers use to increase the amount of data you store in a local area. And the way they do it is by using laser, and locally they heat up that area, and that way they have capability to store more data. But when you think about laser and heating, all of a sudden you think about, oh my God, I'm heating up my drive, so I have to cool it down some way, right? So you have to do thermal management. So the design of experiment that we are introducing is designed around that. So we want to do thermal management for the HAMR technology. And in a real world, when you do design of experiment, you have a lot of factors and levels and responses, so it gets so complex. To keep it simple, we are just looking at 6 factors: cooling technique, material composition, laser power, substrate, ambient temperature, and heat sink design. These are all components that go to thermal management of this technology. And we only define 3 levels for each of these. It can be many, many levels in real world. And we are measuring these 5 different variable responses, like maximum temperature reached, thermal stress, heat dissipation, drive reliability, and thermal expansion. And for each one of these, you want to minimize, maximize, or set at a specific target that we define that in a software. So this is the define part, right? I describe the problem, I define my levels and factors and responses, then I go to JUMP, I put all this information in. And based on different application, you use a physical model behind the scene to now design your experiment. In this case, we use fractional factorial method. You can do full factorial. You can do Taguchi, mixture, mixed mixture things. For different applications, there are different designs. And then when you do that, JUMP gives you sets of experiment to run in a lab. And typically it's like tens to like a lower end of hundreds, right? And then you see it gives me all the factors with the different levels, and I have to go to the lab, put all these combination in place, and then measure all those responses that you see over there. I go, put all this setting, measure this physically. You can imagine the amount of resources and time and effort that I have to go through this exercise. I measure the responses. I ended up with 46 observations for each response that I'm interested to optimize, which you can imagine it's not even enough to like have a good accuracy in modeling. And that's a lot of times that's the case when you are an engineer and you are dealing with design of experiment. That's like, how much data you have, and you have to make a decision based on that. So after we collected this data, instead of just analyzing the data as is, we went to DataMaker. We augment that data with synthetic data really quickly. That's just showing the correlation between our source and synthetic data and the similarity. So the synthetic data is resembling your actual data, and all of a sudden you see all this data distribution. So we had 2 categories of data. We had continuous data like temperature, driver reliability, things like that, and we had categorical data like materials and substrate and like different heat sink designs that they were categories. So you see for the categorical data, you see like the synthetic data doesn't change the bucket, but it adds just the data to that bucket. But the most important part is for continuous responses. You see that where I don't have enough instances, synthetic data is augmenting that data for that bucket that doesn't have enough actual data. And that is very important to improve the accuracy and reveal the actual correlation between my factors and levels. And we took this synthetic data, we went to Waya, and now my colleague Nate is going to show you Waya in action. This is a live demo, so please bear with us if the software is thinking a little bit. The internet here is very slow. It's just a heads up.
Yes, thank you, Nasim. So as Nasim mentioned, this is the outputs from the synthetic data. The design of experiments process has been captured. We captured the responses that Nasim explained in the data footprint that we used. We've expanded the data to account for 10,000 records and 100,000 records, and we've created a baseline between the two. So we're going to evaluate both the design of experiment from a traditional standpoint without synthetic data, and then how we'll capture the delta between the original and the synthetically enhanced design of experiment, and see if we're able to capture insights from the additional data points through the use of synthetic data. So this is the Waya platform. This is within Visual Analytics. We're benchmarking the traditional modeling approach that you would use in your design of experiment software application. In this example, we're showcasing a linear regression model using only one, or evaluating only one response variable. But we're going to walk through and evaluate all the response variables, and again, as Nasim mentioned, combine that into one single metric, which is the desirability calculation. Oh. Hold on.
I told you live demo.
It timed out. Okay, perfect. So on the left, you see here, this is the linear regression model that we've developed in the SAS platform, the SAS Viya platform. And you'll note that it's kind of hard to see on this screen, but you'll note that it's the same type of modeling approach that you would conduct in the JUMP application in this example. It's not limited to JUMP, it can be really any DOE application that to your, whichever DOE application that you're using. In this example, we've chosen JUMP. But we can enhance it further through the use of synthetic data. We've turned this problem into a big data problem, and so now we can use the more sophisticated modeling approaches that are available to us within the Viya platform, including more robust machine learning algorithms, which we've decided to use outside of just the linear regression. So on the top, we have max temperature reached, heat dissipation rate, all the response variables that Nassim had mentioned in the presentation. We can evaluate max temperature reached. As I mentioned, we're benchmarking the results of the synthetic data being tied to the DOE process. So from left to right, we have a traditional, we have the original DOE without synthetic data. We can see the observations, which are 46 unique experiments. We have our variable importance that are specified for this response variable, and then some fit statistics to evaluate the accuracy of the model. This is a gradient boosting model that we're using, so we've transitioned from the linear regression, the traditional approach, to a more robust model. And as we move to the right, we can see the enhancements that are made within synthetic data. So we've had, this middle model is including 10,000 additional data points from synthetic data, or from DataMaker, and 100,000 record from DataMaker. And we're trying to identify any sort of changes with the additional data points that we wouldn't originally capture if we didn't have the synthetic data approach. One thing to call out is ambient temperature, and I can expand this to show the variable importance a bit better. Ambient temperature is the least important factor for the response that we're capturing in this modeling approach. Heat sink design is the most important. Once we add additional data points, we have a more comprehensive view into the data and how it changes with additional data points. Ambient temperature has risen by a point, or excuse me, has risen in the ranks for importance. And it's remained pretty consistent, but that change alone is pretty important. So if you think about it from a DOE standpoint, if you are running the traditional way of doing things, you're operating suboptimally off the bat. You can only do so much with 46 experiments at any given time, or around the tens of experiments for any given time. You're gonna operate your process a certain way over a period of time until you find that optimal approach through running it, typically a year, 6 months to a year, 18 months before you find those set points. In this example, we're able to capture some insights that you just can't capture with the original 46 observations. And there's a better example within the response that show a higher weight to one of these response variables that are captured and move up quite significantly in the ranks for variable importance. So I've switched over to heat dissipation rate as our other response variable that we've built. Same thing, gradient boosting for each one of these steps, 46 observations, 10,000 synthetically data points, and 100,000 synthetic data points. We have substrate material being the most significant or the most impactful. With 10,000 record points, not even 100,000, we have cooling technique actually far outweighing the importance for that factor that's being fed into the DOE. And that remains consistent with cooling technique for 100,000 records as well. And then a last example, again, we've done this for every single response, but to go through this fairly quickly because we have limited time, we're just identifying these factors that change with the additional data points and having a more comprehensive or representative variable importance metric for evaluating what is truly going to be our optimal state or optimal material to use within the DOE. Same thing here, just different patterns within our response variables that we're capturing. Material composition goes up, and ambient temperature also goes up, substrate material goes down. This is going to be more important when I start evaluating the desirability calculations and having a comprehensive, one single metric that we base these decisions on or our optimal solution on.
Can I say something?
Sure.
So think about it. You are an engineering manager, you have a limited budget, you can improve one of these. If you don't have the right correlation from the get-go, you cannot make the right investment. So you are gonna go, around and around, investing on a wrong material that's not gonna improve your design of experiment that much. So that's the message.
So this next example is just a data exploration technique. It's fairly common in applications such as JMP, especially when you're building your design of experiments. We've included this to evaluate or benchmark the results of not only the statistics behind the original response, but also the statistics behind the trained model that we've included into our desirability calculations in the next step. What we're looking for is any sort of abnormalities between the two. We should see similar behaviors after the training process has been conducted or the fit process has been conducted for our original design of experiments. And I can expand this a bit more to showcase what that looks like. Again, the blue is max temperature reach. That's our response variable. That was original before fit. The yellow is our predicted response variable after fit. And then we have our residual, the difference between the two. We're looking for any sort of abnormalities. As an engineer, you can use this as a way of evaluating whether or not the fit is appropriate to move into the desirability calculation. If it's not, then you can always go back and retrain the models or use a different modeling approach that would be more representative for the data that you're using. Once I have done the fit calculations and I'm ready to create that single metric, the desirability calculation, I can go ahead and run this stored process. And behind the scenes, what it's doing is it's building all of the intelligence and the calculations that Naseem mentioned for that desirability calculation. And I'll go ahead and flip back over. This is the output to that result. I can show it in a better way within the dashboard. And so we now have our desirability calculations. We have overall desirability. We've condensed everything into a single metric that we can evaluate what's our optimal solution based on the factors that we're feeding into the design of experiment process. I can break it down a bit better in the desirability calculations and showcase this in buckets. So we can see that in cooling technique, liquid cooling is the most desirable before optimization process. Enhanced heat is the desired or optimal process to use for heat sink design, and so on and so forth. This is a good baseline for understanding, but we need to optimize this going forward. Again, I've done this for base and synthetic data. So my base DOE, we have very similar overall desirability calculations between each one of these factors. Base DOE is around 0.80, which is fairly high. Closer to 1 is better. And then 0.80 for synthetic data. We need to run an optimization process because we've only been able to capture 3 of the values in a range of within a numerical range. So laser power could be any number between 50 to 100, and ambient temperature could be any number between 50 and 30. We want to find an optimal solution that is as close to the pinpoint correct metric that we would apply instead of the 3 values that we included into the design within the design. So I can run my optimization. And behind the scenes, we're going to be running some deep learning models to score the results of our optimization for not only a optimal approach for our factors for each one of the categories, but also the pinpoint set point or the accurate set point within that range of numeric values that it could be. So we have 2 models that were ran. The one is for the base DOE and the other one was for the synthetically enhanced DOE. Very fast run times. The optimization process took less than, I think, 2 seconds to run in total, or actually less than a second in total to run. Some of that was latency. And now we can start evaluating, apologies for the squishing, but we can start evaluating some of these metrics after the optimization process is ran. There we go. Okay, so this is the original DOE evaluation after optimization. You'll note that the original DOE before optimization was a 0.80 desirability score for all of the categories. It's increased to 0.85, which is an increase to the original DOE. So even without synthetic data, we're able to enhance the original DOE approach. But we want to see what the values are for synthetic data. Oh, and I'll also mention that you'll note Before, we had laser power being 50, being most desirable, and ambient temperature being 15. Now we have a true set point within that range, 54.95, and 18.25 for laser power and ambient temperature, respectively. When I flip over to synthetically enhanced DOE, we have an overall desirability of 0.92. 0.92 is much higher than the 0.80 before optimization, so this just proves to us that using synthetic data for this approach, we're able to capture much more insight into and much more, a much better optimized state initially in the stage for DOE versus running a suboptimal solution for a period of time. Substantial cost saving ramifications, substantial amount of time and money that you have an optimal solution for. And we also have also updated metrics for our laser power and ambient temperature. Ambient temperature was 18.25 on the previous example. It's actually closer to 15.4 now for our desired state. So I know that was very quick. This is not a whole lot of time to perform this demonstration. This is normally done for around 40 minutes, but Nasim and I are here to answer any questions, follow up for anyone that has either further questions beyond what we're able to answer in this session or any assistance going forward. But yeah, this is exciting. This is a passion project of Nasim and I. As you can probably see, we're really excited. This is patent pending. And it's just going to further enhance. This is one specific DOE process. We plan to expand this to many other DOE applications or DOE processes as well.
Thank you, Nate. And I just add one thing for engineer. I come from engineering background. This is a huge change from 0.8 to 0.92. That means my product is a lot higher in terms of quality at the end after this design of experiment, or my process is a lot more optimized. You know that 0.1 is a huge drastic change for me. So I just wanted you to transfer that number to the value you get at the end. And thank you so much for your time. Now we can take questions, right?
So much.
Hopefully.
Yeah, we are just about at time. Are there any questions in the crowd? If we can answer them really quick, we've just got a little bit of time. What?
Okay, sorry, my question is going back, how do you generate each response value, the synthetic response value? Thank you.
Yes,
Go ahead. You go.
Yeah, so in the synthetic data application, it's able to generate within one data set all of those response values. So it'll take the original response values. In this case, we applied the SMOTE procedure, and it's going to have a kind of a parameter approach to it and fill in the blanks between. So what we're really expanding is the response values more than anything, right? The factors that go into it are contained. There's only 3 values. We're not doing anything to those, but we're giving more, hypothetically, more experiments that you could conceivably run with the synthetic data, and it's producing those results for response variables. No, they're based on the original data that we feed into the synthetic data application. So the original data is used in the synthetic data. It expands based on the data that we're feeding it, and then we use each one of those response variables in their own fit. Their own model to produce the fit, and then we combine all of those results into the single metric, which is overall desirability.
All right, thank you so much. Any questions? They are available for personal questions after the session. We do have to move on. Thank you so much for everyone. Give it up for Nate and Nasim.
Thank you. And yeah, we would love to answer questions, so we are available.
Yeah.